It is my pleasure to introduce Brittney Marsters from San Diego State University. And she will be first showing us a cool animation and then telling us about optimizing polytopal norms with respect to numerical semigroups.
All right, so my name is Brittney Marsters. And before I can talk to you guys about optimizing polytopal norms or numerical semigroups, I'm going to show you this little animation so that we can keep the big picture in mind. So this little blue kind of codimension 1 simplex here is something called the numerical semigroup polytope. And this little polytope here is going to be a polytope that we say induces a norm value. And I'm going to talk a little bit more about what those are in a second, but let's go ahead and watch this clip. So we begin by dilating our polytope till we intersect. So we would expect integer points here to minimize something. And if we keep going, we see that the kind of last natural intersection is going to happen around the axes. And so we're going to expect values around there to maximize our norm values. So this is the big kind of interplay to keep in mind. My theorems are kind of annoying and like wall of text, but really this is what's happening is you just kind of have a natural interplay of these two polytopes. Okay, so share the actual slides now. Wow, okay. We're going to see it backwards. All right, so this is joint work with my advisor, Dr. Christopher O'Neill. He is known for working with numerical semigroups, so I'm going to talk a bit about numerical semigroups. So first, we're going to talk about polytopal norms. We fix a polytope and an integer point. Then the polytopal norm of that integer point with respect to our polytope is just going to be the smallest dilation factor that we need for that polytope to contain our integer point. Because it's the smallest, it's always going to lie nicely on the boundary. So if we consider the polytope, which is just the convex hull of these subset of points denoted below, and we're going to consider the integer point 9, 6, then the polytopal norm value of 9, 6, as it's just 3 times, it's a scaled up vertex, we just get nicely that it's just 3. All right. We're going to look at specific kinds of polytopes that kind of nicely sit near the origin. So we're going to need that it's non-negative. We're going to need that the origin is a vertex in our polytope, and there's a vertex of our polytope on each axis. Lastly, we're also going to need that our polytope is rational, meaning that the coordinates defining the convex hull are rational points. This is kind of more of a generalization or less of a generalization of things that normally induce a polytopal norm, but we're only going to be looking at them on non-negative integer points, so this is what we really need. So on to our second ingredient, numerical semigroups. A numerical semigroup denoted S is generated by G1 through GK. It's a cofinite subset of the non-negative integers that contains the origin and is closed under addition. Elements of our numerical semigroup can be expressed as linear combinations of our generators, where we take our coefficients to also just be non-negative integers. So for example, if we want to look at the numerical semigroup generated by 2, 3, we're just going to look at all of the non-negative integers we can get by adding up copies of 2 and 3. So we get 0 by definition. We get 2 and 3 because they're our generators. We can get 4 from 2 copies of 2. We can get 5 by adding 2 and 3, and so on. Well, we can consider more generators, right? So we can consider the numerical semigroup generated by 6, 9, and 20, and so on. You can take arbitrarily large number of generators. So we get 0 by definition, 6, 9, 12, 2 copies of 6, and so on. So how do we get the points where we're going to optimize our norm values from? This is going to come from something called a factorization. So if integer point is a factorization of our element, if when we take the dot product with our generators, we get out that element. And we're going to note that set of factorizations as z sub s of n. So let's look at an example. If we fix the numerical semigroup 2, 3 and the element 24, well, 24 is divisible by 2. So we see that we can get 24 as 12 copies of 2 and 0 copies of 3, meaning that the integer point 12, 0 is going to lie in our subset of factorizations. Well, there's more than one way to make 24 with this numerical semigroup. We can also take 9 copies of 2 and 2 copies of 3, giving us that this is our subset of factorizations. All right, in the beginning, I showed you the little animation, and we had that little nice codimension 1 simplex. And I said, really, all this is two polytopes playing well together. So let's introduce the second polytope. So when we fix a numerical semigroup, the numerical semigroup polytope of S, we're going to denote it P sub S, is going to be the convex hull of 1 over our first generator times our first basis vector, all the way up through 1 over our last generator times our last basis vector. And it's always going to be a nice little codimension 1 simplex. So when we fix an element in our numerical semigroup, the factorizations are going to be precisely the integer points lying on the nth dilation of this numerical semigroup polytope. So whenever we want to get a hold of this set of factorizations, we take our numerical semigroup polytope, we dilate it by s, n, and we intersect it with the non-negative integer lattice. So here are some examples. We take 2 generators, we're going to get that nice little line segment, that little codimension 1 simplex. And when we can take it for more generators, we're going to get this nice little triangle sitting out in space. Keep in mind, this doesn't contain the origin. It is codimension 1, so it's just kind of like a little flat little thing hanging out in space. If we want the integer points for an element or numerical semigroup, we're just going to dilate this polytope. Okay, so the other part of this talk is optimizing, right? So we're going to minimize or maximize something. So we got a polytope that induces a norm. We've got a numerical semigroup. We're going to define the max polytopal norm of n as the max polytopal norm value over our set of factorizations. And I'll bring your attention to the superscript, capital M for max. Similarly, we're going to define min polytopal norm as the min polytopal norm value over our set of factorizations. We're going to have the superscript little m for min. Okay, so before we can get into our results, like most things in mathematics, sometimes we put our heavy lifting of our argument into a nice little lemma. And so I looked to where we could extend these polytopal norms to have kind of a nice linearity condition. Can't always do this. It's kind of like in each proper face, the cone over it induces a different norm value. So when you're stuck in that cone over a proper face, we have this nice linearity condition. And what this lets us do is it lets us break up a big problem into a lot of smaller problems. Okay, this was supposed to be the animation. It was made by my friend Ailish O'Reilly. Okay, so this is the first big result. Like I said, bit of a wall of text. So we're going to start with a rational polytope that induces a norm. And the set of vertices are going to be the vertices sitting on the axes. We're going to permute and relabel all of our coordinates in our space to impose this kind of ordering where we take that vertex times our generators. So this condition here is telling us when we dilate a numerical semigroup polytope, where does it agree with the vertices of the polytope that induces a norm? So this condition, I from 1 to j, is just taking the subset of those coordinates that agree with the numerical semigroup polytope. Then we get this nice, eventually quasi-linear relationship. So we see that if we take our element n and we add the LCM of the generators that are going to correspond to the coordinates where it agrees with the numerical semigroup polytopes, it's the same as taking the max polytopal norm value, also taking the generators, and then dividing by t, where t is this factor where we had to dilate our numerical semigroup polytope to make it agree with our polytope. So let's look at an example so that maybe we can make sense of some of this bit of wall of text. So we're going to consider this family of polytopes, and we don't need to completely parse. It's a lot to read, but it's kind of, you'll see some patterns. Basically what this is it's a set of polytopes where it's the unit cube, except on some subset of the vertices where they're going to agree with the numerical semigroup polytope instead. So if we have P sub x, we're going to agree with the numerical semigroup polytope with the coordinate 1, 6, 0, 0, and all the other vertices are going to belong to the unit cube. If we go to P x sub y, again, we're going to agree in this coordinate, but we're also going to agree on the y axis as well. If we go to P sub x sub y, Z, we see that we're going to agree with the numerical semigroup polytope on all 3 coordinates. So if we want to see what this theorem is saying, basically, the first thing we got to look at is these products of our vertices and our numerical semigroup generators. And then what we're going to look for is we're going to look for the smallest values popping up, and then we're going to look for ties. So if we look for our polytope P sub x, we compute our products. We see that the smallest is going to be our V sub 1 and our G sub 1. So what we're going to do is we're going to look for the LCM of just G sub 1 by itself, which gives us 6, right? Well, we didn't have to dilate our numerical semigroup polytope for it to agree with our polytope, so that T factor that we saw earlier is just going to be 1, so we don't have to divide out by anything. If we want to look at something slightly more interesting, right, we can consider the P sub x, y example. It's going to have a tie. It's going to agree with our numerical semigroup polytope in 2 places, in both the x coordinate and the y coordinate. So we've got to take the LCM of our first and second generators, giving us this relationship here. And again, it's not too surprising that the axes are popping up, because when we saw that little animation, right, the norm integer points near those regions, we're going to maximize this norm value. So this is how max norm plays out. Okay. Before we can discuss what happens in min norm, we have to be a little bit more careful here, because the min norm is going to depend on that first initial intersection of our polytope and our numerical semigroup polytope. And we're going to call that the initial tangency. So we fix the numerical semigroup and we fix a polytope that's going to induce a norm. This initial tangency is just going to be the face of our polytope that intersects first, which is what this minimal condition is. So let's look at some examples. So we can fix the numerical semigroup 2, 3, and we're going to consider these 2 polytopes that induce a norm, as we can see pictured here. Well, in this case, we have to dilate our numerical semigroup polytope by a factor 5, and that initial intersection is just going to be that single point there. Okay. Well, over here, if we dilate our numerical semigroup polytope by a factor of 12, we see that this intersection is a proper face of our polytope. As we increase our dimensions, we can have different kinds of initial tangencies, leading to uglier and less fun expressions. One of the reasons we care about this is if we're trying to minimize our norm value, we really want to look at the cone over this initial tangency for the values that are going to minimize it. When we don't have the initial tangency being a proper face, we don't have enough integer points on our numerical semigroup polytope always. So we have to do something a little more interesting. So this leads to my last result, which is how classifying how min polytopal norms work. It's the same kind of result. We get that it's eventually quasi-linear, where eventually just means we're going to have gone far enough out where we're going to get integer points in the cone over that initial tangency. So again, we take a polytope P that induces a norm, and we take a numerical semigroup. We're going to let F be this initial intersection, this initial tangency. We had to dilate a numerical semigroup by a factor of T, and we're going to try and remember that. It's a rational factor because we picked rational polytopes. So we're going to take it in its lowest terms. Then we're going to take another scalar, T prime, an integer, chosen the smallest possible so that we can get this to contain an integer point. Then when we take n sufficiently large, again, we get this nice, eventually quasi-linear relationship. Okay, so what is this actually saying? Again, wall of text. We're going to consider this family of numerical semigroups this time, polytopes, and we're going to fix the numerical semigroup generated by 11, 12, and 13. You'll notice with this family of polytopes, we're just tacking on an extra vertex each time. What this is going to do is change that initial tangency. So we dilate the numerical semigroup polytope by a factor of 121. And we're going to get this set of initial tangencies. So in this first case, it's going to meet at a point. In this next case, it's going to meet at an edge. And in this last case, it's going to meet at a facet. Now, each of these initial tangencies is a different dimension. Each of these polytopal norm values is completely different, but the relationship they're going to induce is the same because we had to dilate it by a factor of 121 each time. Additionally, these already contain an integer point kind of by construction, right? So we don't have to keep track of a t prime factor anywhere. So again, they're all each different dimension, but our t value is fixed. So all three polytopes are going to satisfy this relationship here. Okay, that is it for me. What questions do you folks have?
Okay, let's first thank Brittney again. Okay, and now we have time for some questions.
Can I ask a clarification question? Or I should try to do it in the chat first.
No, there's nothing in the chat right now.
So I'm wondering if I'm a total outsider to numerical semigroups. Does understanding this norm property tell you something sort of helpful about the numerical semigroup itself?
Yeah, so one of the classical invariants that we study is something called max and min length of a factorization. And I had to cut it out because of time constraints, but essentially you look at the largest coordinate sum and the smallest coordinate sum for your numerical semigroup. And you get a lot of relationships that look nice like this. And that kind of helps you pick out specific kinds of factorizations in your set. So we can look for factorizations if you pick a clever polytope, where we have the most flat kind of factorizations and the most skewed in one direction. This is kind of a generalization of that idea.
So I'm maybe a little bit more algebraic than you are. And so I think when I hear the word factorization, I immediately think about like polynomial rings. And I'm wondering if I were to translate this whole statement into the question about just like polynomial rings and ideals and wanting to understand minimal length factorizations, is there a nice way you can phrase your results in that way?
Not that I've explored it, but numerical semigroups do play really nicely with polynomial rings. There's something called, like, you can make a toric variety out of them, and a bunch of binomial ideal results there. And essentially what you do is you kind of find nice relations and you stick them up in the exponent and do some clever quotienting with Betty elements. But there's definitely a lot of connections there.
Cool, thanks.
Right.
Okay. Are there any other questions? I had a question about the specific example that you were using before, where you had this cube and then you were adding like new vertices on the different axes. Are all these polytopes always combinatorially isomorphic to cubes, or is the combinatorial class also changing?
They're gonna be isomorphic. All you're doing is, if you think about, you just take the coordinate on the axes and kind of just dragging it inward.
Mm-hmm.
So you just kind of squish.
Do these play a special role in what you were mentioning before? So are the norms with respect to these polytopes special in what you're studying about the semigroups?
So they're special in the fact that this is kind of the nicest way that I can illustrate the agreeing with the numerical semigroup polytope in all of the different cases. Not every polytope is going to agree like nicely with all possible subsets of your generators. Taking this kind of family gives us the advantage to kind of explore what happens there.
Okay.
All right. Well,
okay, maybe we can leave more questions for the breaks. Let's thank Brittney again for a wonderful talk.